Hi everyone, Christian Aparicio here again to give you another presentation on Nastran Solution 200. Uh, this particular presentation will be focused on automotive applications. My whole goal with this presentation is to really show you what the procedure is like for Nastran Solution 200. If you have a PDF file, how do you convert that to Nastran Solution 200? What are the steps that are necessary to actually perform an optimization? How do you create your design variables? How do you confirm that your model has been properly configured? How do you view results in Excel? How do you view results in, say, your pre-post processor? And then at the end, how do you update your original PDF file with the new optimized parameters, if you will? Before I go ahead and get started, this is part 2 of a 4-part series. Today is May 3rd, which is focused on automotive. Next week, you'll see the same presentation, but that one will be focused for aerospace. That one will be in 1 week at 10 a.m. And then the week after, there will be a presentation on sensitivity analysis with Nastran Solution 200. This will all be done on YouTube Live. So definitely come back in a week so you can see the next presentation. If you want the latest schedule, you can send me an email and I'll definitely get back to you. Just in case you need any more support for Nastran Solution 200, I provide more advanced training. I can give you access to the Nastran Solution 200 web app. I can give you guidance on a project of your own. And it all starts with one email. Again, my email is christian@theengineeringlab.com. And here's what I have as an agenda. I want to go over what size optimization is. There are various types of optimization types out there, and I want to give you an idea of what size optimization is. That's the one we'll focus on exclusively in this presentation. I'll make a brief comment about supported analysis types. I know we have an automotive crowd here today, so your focus might be on dynamic analysis as an example. So I have to really point out what's supported in Nastran Solution 200. And then after that, I'll give you 2 examples that I believe are relevant to an automotive engineer. So I'll present those. And then after that, if time permits, we'll have a question and answer session. Now let's go over what size optimization is. Again, the reason I want to go over this is because there are different types of optimizations out there. And in this presentation, we'll just focus on size optimization. Here, I have a very simple built-up structure. I have 2-dimensional elements here in yellow. If we shrink the elements, we see that there are 1-dimensional elements defined in these green lines also. On first sight, there doesn't seem to be anything too significant in this built-up structure. If we superimpose the dimensions of the elements, or rather the parameters of the elements, we finally see that this structure resembles more a realistic structure that you see here. The 2D elements have a thickness. The 1D elements have beam cross-section parameters that you see here in green. We use parameters to define a lot of these dimensions. A T parameter for thickness, a dimension 1 parameter for the height of the beam, and so on and so on. It is these parameters that can be set as design variables in size optimization. This is a very big difference from the other optimization types. For example, topology optimization. That's the process of just removing material, almost like what a sculptor would do. Shape optimization. That's the process of selecting boundaries that can expand or contract. There is topometry and topography optimization that are very different from size optimization. And again, size optimization is the process of setting a parameter as a design variable. And for the rest of the presentation, this is what I'll be focusing on. If you want more information on the other optimization types, again, you can email me. I'll definitely get back to you. Again, you may be in the automotive industry, so not every analysis type in Nastran is relevant to you. For example, buckling. That's an analysis type you may not be focused on, but you may be focused on normal modes. or any other dynamic type of analysis that you see here on the list. These are all supported in the optimization capability in Nastran Solution 200. So when you look at this, and if you're dealing with a model that's using one of these analysis types, definitely start thinking, how can I optimize this model with optimization? And one or two things I want to point out: fatigue and acoustics. About 4 to 3 years ago, Nastran introduced a built-in fatigue capability through the Nastran Embedded Fatigue module. So you can actually optimize your model for vibratory fatigue or different types of fatigue. But the important thing I want to point out is that you can optimize for fatigue and statics, modes, and dynamics. Also, there was a new module in regards to acoustics, the pore-elastic material module. If you're dealing with trim materials or materials that are produced of pore-elastic materials, you can actually optimize parameters of these PEM materials, if you will. So I just wanted to point out and really get you to start thinking, can I optimize the model I have today? And here, again, I promise to show you what the procedure is like in Nastran. How do you take a PDF file? What's the process to convert it to Nastran Solution 200? How do you view your optimization results? How would you view the results in Patron as another example? And to start off with, we have example 1. This is a model correlation example. There are other names for this. It could be system identification or experimental correlation. There's so many names for this, but here's the basic idea. Here, if you can see this horizontal line, this is a rod fixed on one end and free on the other end. We have the length of the rod as 30 inches, has a cross-sectional radius of 2 inches, and we are performing a modes analysis. So this will produce multiple mode shapes for different natural frequencies. Here in orange is the shape of the first natural mode. And the next plot in the bottom right is the relative displacement of mode 3. So that's in orange. So here in orange again is what the FE model gave as the relative displacements of the mode shapes 1 and 3. Here in blue are what we found the mode shape should be from an experiment. And here in blue are what the relative displacement should have been for the experiment. So here we see that mode shape 1 is sort of far from meeting the experimental mode shape that's represented by these blue dots. And the same can be said about mode 3. The displacements are just not in line with the experimental mode shapes. And what we'll do in this next tutorial, we're going to use the optimization capability to vary some of the parameters in the model so the mode shapes from the FE model match the experimental results. So let me see if I can show you the optimization problem statement. The optimization problem statement is a very critical thing to have before you start with optimization. It describes 3 things. Number 1, what are your design variables? What parameters are you allowing to vary? And in this case, we're allowing the radius of the cross-section to vary. And bear with me while I go ahead and resolve that. So again, the design variables are the parameters that are allowed to vary in your model. In this example, the one parameter we are allowing to vary is the parameter related to the radius of the cross-section. For design objective, we want to minimize the difference between the mode shape and the experimental results. And this is how we are going to do that. We are going to take the root sum of squares of the differences. So here I have this expression defining the objective function. It's defined as the square root of a squared plus b squared plus c squared, where a, b, and c are the differences at these individual points. So for example, at point A, or node 3, we're going to take the difference between the experiment and the FE model, and that will be difference A. Difference B is equal to the difference between the experimental result and the relative displacement at node 6. And C, same expression, but it's for the difference between the relative displacements at node 9. So we're going to define this equation, and the objective will be to minimize this equation. By minimizing this expression, this will help us reduce the first mode shape so it matches the first mode shape for the experiment. We are going to replicate the same thing for our design constraint. So for mode 3, we are going to define this root sum of square expression, where this time the differences will be for mode 3. And then we are going to impose a lower bound saying that this constraint should be less than 0.002. So the upper bound will be 0.002. And now this is what we're going to do. We are going to use the Nastran Solution 200 web app to convert our file to Solution 200. It's going to let us select our design variables, select our objective. I believe I've already created the constraint to save time. Then we're going to perform the optimization in Nastran. We're going to view the results in the F06 file. We're going to view the results in Excel. We're going to view the new mode shapes in Patron just to confirm that we got what we wanted. And then we are going to update the original BDF file with the new parameters. The original BDF file has the old radius of 2 inches. We have to update that so it has the new parameter. So again, we are going to use the Nastran Solution 200 web app. This will take an existing Solution 101, 103, so on and so on, BDF file. It will convert it to Solution 200. It will help you create your variables, your objective, and your constraints. This is traditionally a very tedious process and very confusing if you're new, but the web app makes the process a lot cleaner for you. And now let's go ahead and go through the process. It would probably be a good idea to show you what the results look like in Patron actually. So let's go ahead and start Patron and view this result. The reason I want to show you the results in Patron first, I want to show you what the mode shapes actually look like. And then later on, we're going to view the new mode shape. So let's go ahead and import this model. Definitely think of an example of your own. You may have already built your model in your pre-post processor. You might already have a BDF file ready to go. And again, the goal of this presentation is to show you what the procedure is like to perform the optimization. Just go ahead and run this example so I can produce some results and show you the initial mode shapes. So the mode shapes I'm about to show you are for the original design. So let's go ahead and plot those right now on the screen. So this is mode shape 1. Let me make sure I'm looking at the right. Alright, I am looking at the wrong plane. So if we rotate this, there we go. So here's the first mode shape. You can see it's a bending mode shape. And then mode shape 3, that is an extensional mode shape. So it's going in and out. Maybe I can actually animate that if this lets me. So here's the third mode shape. And then the first mode shape is here. Again, what we want to do is modify a parameter so the mode shape better matches our experimental mode shapes. And now let's go ahead and walk you through the process of doing that. To start off with, on my desktop, I'll go ahead and create a new folder called Optimization Working Directory. This is where I'll keep all my files for the optimization. I will also open a web browser and I'll navigate to the web app. So here, let's go ahead and go to that right now. Now to start off with, take the BDF file you may have created. So here is the BDF file on the right. Select all the text that's in there, copy it, and then paste it in the web app. So we'll go ahead and do that now. And the first thing the web app will do is identify all the parameters that can be set as design variables. And here you can see there are numerous design variables I can set. I can set the Young's modulus, the Poisson ratio, the density. I can set the dimensions of the rod elements as design variables. Here I'm interested in setting dim1 as a design variable. So we can click on the plus sign to reserve it as a design variable. So let's go ahead and do that. In the next table is where our newly created design variable is placed. And now all we have to do is place our limit, saying this design variable of the radius can range between 0.1 and 10 inches. So we'll go ahead and type 10.0 there. And that completes the creation of the design variable. Let's move on to creating our design objective. So here, we want to create a synthetic objective. This is a custom equation that we want to set. And the first thing we have to do here is define A, B, and C. And then we're going to create this expression F. So square root of A squared plus B squared plus C squared. So the first expression is 0.01843. So let's go ahead and copy that for now. So here in the next table, we need to create our value R801, which is the displacement at node 3 for mode 1. So in this table, this is where you can define that. So let's go ahead and click on displacement to create my new displacement constraint here. This is being applied to mode 1, grid 3, and I want to track, what was I tracking here? I think it was a Z displacement. At Patron open so we can check. Yes, the Z displacement. So that would be the third component. Third component, T3, rectangular Z coordinate, if you will. So that creates that expression. Now here in the equation for F, I can type in the square root of some expression. And the first value is going to be A squared. So here R801 corresponds to the label here R801. And throughout this demo, you'll notice that the web app is automatically creating my bulk data entries that I need for Nastran Solution 200. I don't have to generate these by hand. I don't have to create an elaborate script to create these for me. The web app is taking care of this for me. If I make an edit here, for example, instead of node 3, I want to say node 100 or 999. The web app will instantaneously update the bulk data entries for me, and I really don't have to worry about maintaining these entries. The web app, again, does it for you. Now, let's continue on creating our expression. So the next part of the expression is B squared, so that would be 0.1741 minus R802. So let's go ahead and type that here. So plus, and let me zoom in actually so you get a better look. So R8 plus this expression B squared. And then we have to define R802. So here we'll create displacement. In the next table, we have our newly created displacement constraint. We're going to constrain this in the Z component or third. This is mode 1 for grid 6. And then we can carry on after that. The next expression is C, so that would be this here. So we'll go ahead and copy that. Minimize this, and then we'll go ahead and paste that here. So plus squared. And then we'll go ahead and create a new displacement constraint. So we'll click on this plus icon. We'll select the third component for grid or mode 1 for grid 9. And let me confirm that it is node 9. Yeah, node 9. And now this is going to produce a root sum of squares value. And what we want to do is minimize this as much as possible. When that happens, it will vary the parameters so the orange line is right on the edge of the blue points. So now let's go ahead and define our design constraint. Here, if we scroll down the page, there is a section called synthetic constraints. And if we click on the plus icon, this is where we can now define a custom equation for our design constraint. So that would be the square root of d squared plus e squared plus f squared. So now we'll go ahead and define this expression. So let me first copy d. And you'll notice that d needs the value R501. So let's go ahead and create R501. Right underneath the synthetic constraints table, there's a section where you can define these individual responses. So here, let's go ahead and define displacement. Here's R501. This is for mode 3. And I believe the component is component 1. First component, yeah. So we'll go ahead and select T1 or rectangular X. This is for mode 3, mode 3. So this is defined a single value for the relative displacement at grid 3 in the one direction or X direction for mode 3. So now let's go ahead and type in our expression here for the constraint. So the square root of some expression where the first part is squared, and then we'll go ahead and repeat the process for E and F. So let me copy E. And you can see E is using the experimental value of 0.5431 minus R502. Now let's define this term R502. In the same table, we'll go ahead and create a second displacement value. We'll go ahead and select T1. This is mode 3. But this is for mode 6. And then our expression here, we'll update it so it includes this. And then we'll go ahead and do this for the last component. So then F. So we'll go ahead and copy that. We'll repeat the process. Create a displacement. We want to apply this to mode 9, mode 3, X displacement. So this is giving me the value or the relative displacement at node 9 in the X direction for mode 3. And then we'll use all of these in our root sum of squares expression that you see up here. So let me go ahead and complete this expression. And then for our upper limit, we want to make sure that this does not exceed 0.002. And now that completes the creation of our synthetic constraints. Now let's go ahead and create our constraint group. Here we'll click on create a constraint group for all the constraints. So we'll click on add all constraints group, and we'll apply this to all the subcases. And now we can go to the exporter. The exporter has converted our original file from solution 103 that you see here to solution 200 that you see here. It has a reference to the analysis type we want to optimize for. It has a pointer to the objective. It has a pointer to the design constraint. Here on the right are the statements for the design model. I have the design variables, the design objective, and the design constraints here all created for me. I didn't have to type out any of this for me. Go ahead and download both of these files to my desktop so we can perform the optimization. So let me go ahead and delete these old files, and we'll go ahead and click download here and here. And here are my two new files. Again, this is the converted version of the 103 file, and the design model has my design variables, constraints, and objective. There's one modification I have to make, and I'll detail that now. It's the ModTrack modification, and here's the significance of using this edit. Here on the left is the original mode shapes. So mode shape 1 is bending, bending, extensional, bending again. Let's suppose that during the optimization, a new parameter is found that's optimal. Mode 1 has the same mode shape as before. Mode 2 is still bending. Mode 3 is now bending, whereas before it was extensional. Mode 4 is now extensional, whereas before it was bending. What we've done with the design constraint equation as an example, we've applied that constraint to mode 3. So to begin with, that constraint is being applied to an extensional mode shape. But then after or during the optimization process, this mode shape has a higher natural frequency, so the mode number is mode 4. But the constraint is still being applied to mode 3, which is something we probably don't want. What ModTrack does, if a mode shape were to have a higher natural frequency and its mode number changes, here in this case mode 3 becomes mode 4, ModTrack keeps track of this change. So the constraint that was originally applied to mode 3 follows the mode shape and is now being applied to mode shape 4. So now how do you do that in this example? You will have to open the BDF file in Notepad to make the modifications. So here, zoom in and under subcase, type in ModTrack 800. And then here under begin bulk, add a new line called ModTrack, 800, 1, 100. And then we'll save this model BDF file and we'll run the optimization. So again, this edit was necessary so we make sure that the design constraint is being applied to the correct mode shape. So we'll go ahead and let it do its thing. And one thing I want to do right now is prepare my Excel template. Your optimization results can be viewed in the F06 file. Alternatively, they can be viewed in the comma separated value. And here, let's first open the F06 file. And here, what we want to do is make sure that we have a successful optimization. Here, it seems I've encountered an error. So let's go ahead and fix that right now. So here it seems that these minuses are not minuses, they're actually hyphens. When I copy this from PowerPoint, the symbols here must have been minuses. Yeah, these are hyphens here. This is what a minus symbol looks like. So what I have to do here is change these hyphens to minuses. So we'll go ahead and do that here and here. And we'll do the same for the objective. So we'll go ahead and update these. And again, the way I knew this, I inspected the BDF file for a user fatal message. And then here it says illegal character encountered on line 31. And you can see that the hyphen has become this sort of weird set of 3 characters. So the correction was to go back to the web app and make sure that these are minus signs here and here. So now let's go back to the exporter and download this new BDF file. And then I'll delete everything from here except for the design model. And then I'll go ahead and copy this new design model and paste it in my optimization working directory. We'll go ahead and redo this analysis. Again, if you have any questions, comments, feel free to leave me a question in the chat window and I'll definitely address that. Alternatively, you can send me an email at, here, let me see if I can show you, christian@theengineeringlab.com, and I'll definitely get back to you. And now let's go ahead and view if we've had a successful analysis. And here what I have to do is close some of these applications and rerun the analysis. And in a moment, we'll go ahead and view the results in the F06 file. It's always important to search the F06 file for any fatal messages. And here there are no user fatal messages, so this is a good sign the analysis went through successfully. At the very bottom, there's a table regarding the summary of your optimization. Here at the bottom, you should find this message: run terminated due to hard convergence at an optimum. This is indication that you've had a successful message. Here in this table, you have a column for the objective. These values are the actual root sum square values for your objective function f that we've defined. In this table, this is reporting the changes in your design variables. Again, we started with the value of 2 inches for the radius, and we ended at a value of 3.93. Now, let's go ahead and view these results in Excel. I'll open the CSV file and move it to the left, and then I'll open the Excel file on the right. And all I have to do is select the text from the left and paste it here on the right. And now you can see here is a plot of my RSS value. We started with the value of 0.1978. We needed to minimize the RSS value as much as possible, and we eventually got to a value of 0.0002. My design variable started at a value of 2 inches. It went up to a value of 1.093, and then it ultimately ended at a value of 3.93 inches for the radius. Here, the headings on the x-axis or horizontal axes are not accurate. To better represent these columns, you can shift these headers up one. This would be your initial design, and this last one would be your optimized design cycle 4. So then I can go here and edit the data and modify the X labels. So here, this will probably be better to understand. Here is my initial design radius. After 1, 2, 3, and 4 design cycles, I land on my optimized design cycle 4, of a value of 3.93 inches for the radius. So that's how you view the values in Excel. That's how you view the values in your F06 file. So these same values were reported in the CSV file. And now let's go ahead and view the results in Patran. So let's go ahead and delete the old result file, and then I'll attach the new result file. During the optimization, you have a number of files created. You have the CSV file created. You have a new result file created, which is what I'm attaching right now. When you look at the result file, you have double the set of data. So here, for example, here is the original mode shape for the original design. And I know it's the original design because I get a D0 here, which corresponds to the initial design. I also have a D4, which is the final design cycle, which was optimized. So if I go ahead and look at this optimized mode shape, you notice that the middle is slightly different, and just keep looking here and you'll notice it shift. You notice that it's a little bit more inward, if you will. And then rather than look at the other mode shape here, I'll go ahead and look at my PowerPoint. That better communicates what I'm trying to say. Again, the whole point here was to vary the cross-section radius so that the mode shape matched what we expected from the experiment. And here are the results. Here in orange is the FE model original mode shape. Here in gray is the optimized mode shape for mode 1. And you can see that it's now aligned to the experimental results in blue. The same is true for mode shape 3. Here is the relative displacement of mode shape 3. Remember, this was an extensional mode. Here in gray is the new relative displacement for mode shape 3. And you can see that it's matching the blue experimental points. So we've achieved the goal of finding a new parameter for the radius. And now the last thing I want to show you for this example, how do you update the original model? So let's go ahead and go through the process. So we'll start off with the new directory called 3 optimized model. I'll call it updated model. And then this is the one I want. So here on the left, I'm going to open the original BDF file, and here on the right, I'm going to update, show you what the one we want to update. So you can see that for the P bar L entries, they still have a value of 2 inches and 2 here. Our new value is 3.09 or 3.9, I forgot the value. These entries are created or updated in a new file called a punch file. So let's open that punch file. Here you can see that for P bar L1, it's updated the 2 inches to 3.93 inches. So the perfect thing about this is I can simply take this value, cut it, copy it, and then here on the right, I can simply replace that entry with this new entry, and there we have it. Of course, we'll save it. And now here, if I look inside of the updated model directory, this DAT or BDF file has been updated with the new P bar L entry. So I can hand this off, I can give it to another engineer, I can archive it, knowing that this is the optimized version. So that's the procedure from beginning to end. I noticed we're 40 minutes in, so we'll see if I can go through the next demonstration. I expect this one to maybe take the rest of the hour, so it might take 20 minutes. Just in case you have to run off to a meeting, or if you have to run off for another errand, there will be a recording to this presentation, so definitely come back to the YouTube channel and you'll find the recording within the next hour after this presentation is over. And now let me go ahead and walk you through this next demonstration. This one's a little bit more abstract, I guess. So let's go ahead and go through what the process is. So this is another example you might encounter in the automotive industry. We have a hypothetical car is subjected to a dynamic loading. We perform a dynamic analysis, and what we want to do is help control the RMS value at the center of gravity. We want to make sure that's within a certain limit. This example happens to be from the Nastran Sensitivity and Optimization Users Guide, Chapter 8, RMS Response. If you want full details of this, definitely refer there. In this next few minutes, I'll very lightly cover it. So again, what is our optimization problem statement? It's very important that we have this before going in. The first thing are the design variables. Here, what we want to vary is the stiffness in the shock absorbers. We want to vary the damping in the shock absorbers also. For the design objective, we want to minimize the RMS value of PSD displacement at node 5. And for the design constraints, we want to make sure that the beam members, again, this is a very simple model, the beam members that are connecting from node 1 to 5 and 5 and 2 are within a value of 45,000. So let's go ahead and show you what the before and after is. Here in orange is what the PSD displacement at node 5 looks like for the various forcing frequencies. By minimizing the RMS value of displacement, this will produce a new PSD displacement function that you see here in blue. And you can see that the area underneath is a lot lower than it was before. So here in blue is what we're ultimately going for. The stiffness and the damping goes from 202 to 110. And now there's a lot to cover here. I won't show you how to do this or how to view the results in Excel or Patron or any of that. What I want to do is show you how to confirm that you've properly set your values. Once you optimize large models, you want to make sure that you've properly configured your design variables, your design constraints or your design objective, every now and then you may have singled out the wrong design variable. Maybe you selected, viscosity when you meant to select stiffness as an example. I'll show you what the checks you should do to make sure you prevent things like that. So now let's go ahead and go through the process. I'll move this to the left. I'll go ahead and delete my old files here. Let me move this a little bit. And for demo 2, let's go ahead and create our optimization working directory. So go ahead and open this to optimization working directory. And then to start off with, let's go ahead and open the dat file. So this file has a description of the entire car model, if you will. What I need to do now is use the web app to construct my design model. So here, let's go through the process of doing that. First thing I'll do is I'll copy and paste my BDF file here. I'll click on this button so the web app identifies all the properties that can be set as design variables. I'll search the list for K so we can find our stiffness and set it as a design variable. So we'll go ahead and do that now. And then we want to do this for damping, which is represented by the B2 property. So we'll go ahead and set that as a design variable also. Here are the new design variables. I'll type in my lower bound and my upper bound here. I'll do the same for the damping. So 1 and 10. Next, let's go ahead and create our objective. So here, I want to look for RMS displacement. So I searched the table and I found a root mean square response. I'll set this as an objective. And now let's go ahead and configure this objective. We want to minimize the displacement in the Y direction. So that would be a rectangular Y, or the T2 or the second item code. So we'll select 2 there. We'll select this for grid or node 5, which is the center of gravity for the vehicle. So again, let me go back to this example. So here in the diagram is our vehicle. It's composed of 5 nodes. Node 5 happens to represent the center of gravity, and this is where we're interested in the displacement. And then the RAN PS ID. This is referring to the ID that was used to define your PSD input. So here, if we scroll down, that would be here. You would use the ID 1000 that you find here. So we'll go ahead and type in 1000 here. And that completes the creation of our objective here. Again, we want to minimize the RMS displacement at node 5 in the Y direction for random loading 1000. Let's go ahead and create our constraints. So here we want to create some stress constraints, or more importantly, these are frequency stress constraints. So we'll go ahead and select this one time. And now we'll go ahead and type in our property type. We'll go ahead and type in P bar L. And then we want to apply this to P bar L11. And then what quantity do we want to constrain actually? Here, what I want to do is constrain NB.C. So I want to constrain the real value of NB.C. And then I want to do this for all the natural frequencies. So here you can specify a specific forcing frequency. So say you want to minimize, or you want to constrain the frequency stress for forcing frequency 100 hertz. That's how you would type that in. But say you want to make sure that for all the forcing frequencies, the stress is under a certain limit. You can just leave that value blank and it will assume you want to apply this to all the forcing frequencies. Now for the upper bound, we want to type in 45,000. And then we'll repeat this process for the next property type. So we'll type in P bar L, so I can copy that here. And then this will be for end A, so we'll go ahead and select 14 actually. Oh, sorry, end E. So you might be asking, what is D, E, F, and all that stuff? Let me show you what that is right now. Hopefully my drawing skills are really good here with the mouse. So here from 1 to 5, let's go ahead and draw a line. So let's draw a line. Here's node 1, node 5, and node 2. So here's 5, and 2, and 1. So here we have a beam element, but we don't know what the cross section looks like. So let's go ahead and imagine the cross section looking like this for a moment. And then I'll go ahead and see if I can draw this three-dimensionally with the tools that I have. So this will have a end A and the end B. So end B. And you'll notice that there are four corners, that is, for the cross section. There is a corner C and a corner F. Corner E, I should say. So what we're seeing with the constraints we just defined, we expect a linear distribution for the stress throughout the thickness, so we can assume that C is corresponding to the beam stress at the top fiber, and E is corresponding to the beam stress at the bottom fiber. Hence, back in the web app, we went ahead and selected endpoint NB point C and NB point F. So that's what that means. And then let's go ahead and finish this up. This is for P bar L11, and we want to make sure that the frequency stress is always less than 45,000 for all the forcing frequencies. So then we'll go ahead and create our constraint group, apply this to all subcases, and then we'll go ahead and go to the exporter and download both of these files. I won't perform the optimization in this example. Again, what I want to do is describe the procedure to verifying the results. So to start off with, open the design model, and here where the design max is 40, set that to 0. This will force Nastran to only go through the 0 design cycle. We'll go through the first initial analysis. The other thing we should do, let me see if I have that here, is the D-screen option. Let me see if I included that here. And that is not in here, but we'll see if that is available when we perform the optimization. Let's go ahead and copy these files to my optimization working directory. And then I'll go ahead and run Nastran. Again, we want to validate and verify we've properly configured our model. We don't want to perform the optimization just yet. So what we'll go ahead and do is open the F06 file. The first thing we'll do is we'll look if there are any fatal messages. There are none. So then the next thing we'll do is look here. The message now says run terminated due to maximum number of design cycles. Perfect. That's what we wanted. We didn't want to go through the very time-consuming process of optimization. We just wanted to produce the first optimization cycle and verify our results. So if you look at the very top of the F06 file and you scroll down, there'll be a first section where you can validate your results. This first table, that's called comparison between input property values from analysis and design models. This will compare the results from your design model. So if you create a design variable in your web app, as an example, it will take that value and compare it to the value from your original model. Here in this column are the design values for variables stiffness and damping. You can see they're defined as 202. And here for the analysis model, they are also 202. And my difference flag is none. So it's perfect. That says that I properly configured my design variables. Sometimes if a mistake was made, for example, in the web app, I misconfigured my design variable. And here I'll have a difference. Here, for example, I'll say 1 and it should be 2. You'll get a new flag called warning. Sometimes if the difference is very high, you'll get a fatal, I believe is the message. Yeah, fatal. So if you see warning or fatal, you should look at the warning and see if there are any big differences. Sometimes what you might have happen is it might be a 1.99 and that 0.00001 difference might trigger a warning message. So sometimes you can ignore it if it's a warning. But if you see a fatal, that means something has been completely misconfigured, and you should definitely look at that. Let's scroll down the list and confirm the next thing. And here I have a list of things I want to confirm. So the RMS displacement. So let's go ahead and look at that. I've already taken time before this example to find what the first RMS displacement should be for the original design. So here, let's go ahead and see if we can validate what that is in this example. There's a section that says summary for initial design or initial analysis. Here is where I get the first output for my objective value. So here, the RMS displacement at node 5 is given to me as 1.906. So perfect. I know that I've properly configured my objective value. If here back in the web app, say I accidentally selected the Z component, this will cascade down and it could potentially produce a new value here, 2.5 as an example. And here I could have matched this value with my intended value of 1.9. I find here that it's 2.5, and then I could backtrack it to the web app and see, oh, this should have been component 2. And now let's go ahead and view this for the constraints. And one thing you'll notice here is that the displacement constraints are not outputted here. So I have no way of confirming that my stress constraints have been properly configured. To account for this, we have to make one adjustment. So let's go ahead and go to my optimization working directory, and let's go ahead and delete all of these files. In your design model, you need to add a new line called design constraints. So we'll go ahead and add dscreen. And what is this? FRSTRE. We'll say keep normal constraints to have a value greater than -1000, and then we're going to do this for 1000 or 1 million constraints. So Nastran has a way of screening your constraints. If the constraint is far from being violated, Nastran essentially ignores that constraint and only considers constraints that are right at the edge of being violated. With the dscreen option, that's relaxing the constraint tolerances. So it expands what constraints are retained. The benefit of doing this is that when we look at the initial analysis design summary, we now have more results for the constraints. So here, for example, let me see if I have a verification here. For foresee frequency 0.1, the stress in element 5 should be 5.844. And let me see if I can find that here. So this section here are normalized constraint values. These are not actual stress values. They're not PSI or Pascal values. These are normalized constraint values. Scroll down, and here you'll find a table called responses. And here there are a lot of foresee frequencies, so there's a lot of data here. Here we go. Responses in design model. This is where you actually have values reported for the stress values. This is where you should check to confirm that you properly configure your frequency stress value. So here I expect for forcing frequency 0.1 for element 5 to have a value of 5.844. So we'll look here for forcing frequency 0.01. That would be here. Element 5. And here we can see that we have a stress value of 5.844. So perfect. I've defined my frequency stress constraint properly here. Back in the web app, suppose that we misconfigured our constraint. So here, for example, instead of using the real value, I've set it to the imaginary value of 16 for the atom code. So that would be 16 here. And here we'll report 16 in the right-hand side. This would cascade down to here, and it could report a completely different value. It might report a value of, I don't know, 1.999. And so by doing this validation step, I can look here and confirm, oh, there's an error here. I must have selected the wrong component. Here it would say component 16. Then I can backtrack it to the web app, change the 16 back to 15. Or was it 12? It was 12. And then rerun the optimization and find that the component now says 12 and the value now says 5.84 as intended. So there you have it. That's how you perform a validation in Nastran. Once you've validated that everything's been configured, now we can go ahead and change the design or maximum design cycles to 40. And we can omit the D screen. And now we can perform the optimization as intended. So let's go ahead and do that. And then we are close to this presentation. Again, if you have any questions or comments, feel free to leave me a question in the right-hand chat box. You can send me an email. Maybe I'll type in my email here. And if you send me an email, I'll definitely get back to you. Here I've just performed the optimization. Let's go ahead and go to the very bottom. And well, first we should make sure that there are no fatal messages. Here, the fatal is just a random fatal message. I shouldn't say fatal. It's a comment here. What you should look for is user fatal message. That's the one you should look for. If that's there, that means there's something wrong. Since it's not in this file, we can now confirm our message. Run terminated due to hard convergence. Perfect. We see the RMS value go from 1.9 and it goes to 0.1623. We see the design variables go from 200 to 2 and go to 110. And I believe that's what I have here. Perfect. So there you have it, the before and after. The biggest thing from this tutorial I wanted to show you was, one, how to use the web app to create your design variables, your objective, and your constraints. And number two, how to validate that you've properly configured your variables, your objective, and your constraints. The validation is very important when you launch a full-blown optimization of, say, a big vehicle or a substructure. You want to make sure you've done everything properly up front before you commit possibly days of worth of optimization with your high performance computing hardware. So with that, let's go ahead and start concluding this presentation. Just as a reminder, we went through what size optimization was. Keep in mind there are various types of optimization types out there. This presentation focused on size optimization. We went through what the supporting analysis types were. Most likely, if you're performing a linear type of analysis, whether it's statics, modes, or dynamics, you can perform size optimization. We went through two examples that you might encounter in the automotive industry. You might be asked to correlate your FE model to experiments. We saw a very simple example of that. We saw how to use the web app to create our design variables, objective, and constraints. We went through another example. If you're performing some sort of frequency response analysis and you want to minimize an RMS displacement, we went through what the procedure was, and more importantly, we went through what the validation process is like. We always want to make sure we've properly laid out everything. And then just to finish off this presentation, again, this is part 2 out of a 4-part series. Next week, we are going to do a presentation on aerospace, so definitely check back in 1 week for that version. This is all on YouTube Live. If you want the latest schedule, feel free to send me an email and we'll get back to you. If you want more advanced training, guidance on a project of your own, if you want access to the web app, you can send me an email here and I'll definitely support you. With that, I want to give everyone a big thank you for being with me. If you have any questions or comments, you can send me an email here. I'll stick around for 5 minutes here. There will be a recording of this presentation about an hour after this presentation ends. And again, thank you for being with me today, and then I'll stick around for questions or answers. Thank you.